Hello and welcome. In this video, we will explore how to calculate angles in three-dimensional space, a key topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to: first, find the angle between a line and a plane. Second, find the angle between two intersecting planes. And third, solve more complex problems involving these concepts, including determining if lines and planes are parallel or perpendicular. We will focus on clarity, rigor, and the problem-solving techniques required for the IB exam. Let's begin. Our first objective is to find the angle between a line and a plane. Let's consider a line with a direction vector, which we'll call D, and a plane with a normal vector, nin. The direction vector, D, tells us the direction of the line, while the normal vector, nin, is perpendicular to the plane. Notice the diagram. We have two angles here. The angle between the normal vector, n, and the direction vector, d, is labeled theta theta. The angle we are actually looking for, the angle between the line and the plane, is labeled phi phi. How are these two angles related? Since the normal vector, n, is perpendicular to the plane, the angle between n and the line is complementary to the angle between the line and the plane. This means their sum is 90 degrees. So phi plus theta equals 90 degrees. This is a crucial relationship. We can find the angle theta using the dot product formula for vectors. The cosine of theta is the absolute value of the dot product of 9 and VD divided by the product of their magnitudes. We use the absolute value to ensure we get the acute angle between the vectors. Now, we need to connect this back to phi. From our complementary relationship, we know that cos theta is equal to sine phi. Therefore, we can substitute sine phi for cos theta in our formula. This gives us the formula for the sine of the angle between the line and the plane. It's the absolute value of the dot product of the normal and direction vectors divided by the product of their magnitudes. To find the angle phi itself, we simply take the inverse sine of this expression. So the angle phi is the inverse sine of the absolute value of the dot product of n and diaph d divided by the product of their magnitudes. This is the formula you need to remember. Let's apply this formula to an example. We need to find the angle between the plane x plus 2, yz equals 8, and the line with parametric equations x equals t, y equals 1 dash t, z equals 3 plus 2t. First, we need to identify the normal vector, n, for the plane, and the direction vector, d, for the line. For a plane in the form ax plus by plus cz equals d, the normal vector, n, is simply the vector of the coefficients of x, y, and z. So for our plane, the normal vector n is 1, 2, minus 1. For a line in parametric form, the direction vector, d, is the vector of the coefficients of the parameter t. Looking at our line equations, the direction vector, d, is 1, minus 1, 2. Now we have our two vectors. Let's calculate their dot product and magnitudes. The dot product, n dot d, is 1 times 1, plus 2 times negative 1, plus negative 1 times 2. This simplifies to 1 minus 2, which equals negative 3. The magnitude of n is the square root of 1 squared plus 2 squared plus negative 1 squared, which is the square root of 6. The magnitude of d is the square root of 1 squared plus negative 1 squared plus 2 squared, which is also the square root of 6. Now we can plug these values into our formula for phi. Phi equals the inverse sine of the absolute value of negative 3 divided by the square root of 6 times the square root of 6. This simplifies to the inverse sine of 3 over 6, which is the inverse sine of 1/2. The angle whose sine is 1/2 is 30 degrees, so the angle between the plane and the line is 30 degrees. Now let's move on to our second objective, finding the angle between two planes. This is a very similar process. Suppose we have two planes, plane 1 and plane 2, with normal vectors n1 and n2 respectively. The key insight here is that the angle between the two planes is the same as the acute angle between their normal vectors. Let's visualize this. Imagine two planes intersecting. Now draw a normal vector for each plane. The angle between these two normal vectors is the same as the angle between the planes themselves. This is a fundamental geometric property. Therefore, we can use the dot product formula directly to find this angle. The cosine of the angle theta between the planes is the absolute value of the dot product of their normal vectors, n1 and n2, divided by the product of their magnitudes. Again, we use the absolute value to ensure we find the acute angle, which is the standard convention for the angle between two planes. To find the angle theta, we take the inverse cosine of this expression. This is the formula for the angle between two planes. Let's work through an example. We need to find the angle between the planes x plus y z equals 8 and 2x, y plus 3, z equals minus 1. First, we identify the normal vectors for each plane. For the first plane, the normal vector n1 is 1, 1, minus 1. For the second plane, the normal vector n2 is 2, minus 1, 3. Now, let's calculate the dot product and magnitudes. The dot product n1 dot n2 is 1 times 2, plus 1 times negative 1, plus negative 1 times 3. This gives us 2 minus 1 minus 3, which equals negative 2. The magnitude of n1 is the square root of 1 squared, plus 1 squared, plus negative 1 squared, which is the square root of 3. The magnitude of n2 is the square root of 2 squared, plus negative 1 squared, plus 3 squared, which is the square root of 14. Now we substitute these values into our formula for theta. Theta equals the inverse cosine of the absolute value of negative 2 divided by the square root of 3 times the square root of 14. This simplifies to the inverse cosine of 2 over the square root of 42. Using a calculator, we find that theta is approximately 72.0 degrees, so the angle between the two planes is about 72 degrees. Let's tackle a more complex problem that combines these ideas. We'll use a problem from the exercise set. The problem states, the line L passes through points A, minus 3, 2, 5, and B, 0, 2, minus 1. The plane pi1 has the equation 4x Nash 2y plus 5z equals 16. We need to find the angle between line L and plane pi1. To find the angle between a line and a plane, we need the line's direction vector and the plane's normal vector. First, let's find the direction vector, d, for line L. We can do this by finding the vector from point A to point B. The vector AB is found by subtracting the coordinates of A from the coordinates of B. This gives us the vector 3, 0, minus 6. This is our direction vector, d. Next, we find the normal vector, n, for plane pi1. From the equation, the normal vector is 4 minus 2, 5. So n equals 4 minus 2, 5. Now we have our two vectors. Let's use the formula for the angle phi. Phi equals the inverse sine of the absolute value of the dot product of n and d divided by the product of their magnitudes. The dot product is 4 times 3 plus negative 2 times 0 plus 5 times negative 6. This is 12 minus 30, which is negative 18. The magnitude of n is the square root of 45. The magnitude of d is the square root of 45. Plugging these in, we get phi equals the inverse sine of the absolute value of negative 18 divided by the square root of 45 times the square root of 45. This simplifies to the inverse sine of 18 over 45, which is the inverse sine of 2 over 5. Using a calculator, the angle phi is approximately 23.6 degrees. So the angle between line L and plane pi1 is about 23.6 degrees. Let's look at another important concept, parallel and perpendicular lines and planes. This is a common type of question in the IB exam. First, let's consider parallel lines and planes. A line is parallel to a plane if its direction vector, d, is perpendicular to the plane's normal vector, nen. Think about it. If the line is parallel to the plane, it never intersects it. This means the line must lie in a plane that is parallel to the given plane. The normal vector, n, is perpendicular to the plane, and therefore it must also be perpendicular to any line that is parallel to the plane. Mathematically, two vectors are perpendicular if their dot product is 0. So a line is parallel to a plane if and only if the dot product of its direction vector, d, and the plane's normal vector, n, is 0. Next, let's consider perpendicular planes. Two planes are perpendicular if their normal vectors are perpendicular. This is a direct application of the geometric principle we discussed earlier. The angle between two planes is the same as the angle between their normal vectors. If the planes are perpendicular, the angle between them is 90 degrees. Therefore, the angle between their normal vectors must also be 90 degrees. So two planes are perpendicular if and only if the dot product of their normal vectors, n1 and n2, is 0. Let's work through an example to solidify these concepts. We'll use problem 2a from the exercise. The problem asks us to show that the line x equals 1 plus 3t, y equals 4-t, z equals 2 plus 4t is parallel to the plane 2x plus 2y, z equals 5. To show they are parallel, we need to show that the dot product of the line's direction vector and the plane's normal vector is 0. First, let's find the direction vector, d, for the line. From the parametric equations, the coefficients of Flechter give us the vector 3 minus 1, 4. Next, let's find the normal vector, n, for the plane. From the Cartesian equation, the coefficients of x, y, and z give us the vector 2, 2 minus 1. Now let's calculate their dot product. The dot product, d dot n, is 3 times 2, plus negative 1 times 2, plus 4 times negative 1. This is 6 minus 2 minus 4, which equals 0. Since the dot product is 0, the direction vector, d, is perpendicular to the normal vector, n. This means the line is parallel to the plane, as required. Let's try another example, this time with perpendicular planes. We'll use problem 6 from the exercise. The problem states, the planes x plus 5, y dash 3z equals 8, and 2x plus 2y plus k z equals 9 are perpendicular. Find the value of k. We know that if two planes are perpendicular, their normal vectors must be perpendicular. This means their dot product must be 0. First, let's find the normal vectors for each plane. For the first plane, the normal vector n1 is 1, 5, minus 3. For the second plane, the normal vector n2 is 2, 2, k. Now, we set their dot product equal to 0 and solve for k. The dot product n1 dot n2 is 1 times 2 plus 5 times 2 plus negative 3 times k. This equals 2 plus 10 minus 3k, which simplifies to 12 minus 3k. Since the planes are perpendicular, this dot product must be 0. So 12 minus 3k equals 0. Solving for k, we get 3k equals 12, which means k equals 4. So the value of k that makes the planes perpendicular is 4. Let's recap what we've learned today. We've covered the essential methods for finding angles in 3D space. First, we learned that the angle phi between a line and a plane is found using the inverse sign of the absolute value of the dot product of the normal vector, n, and the direction vector, d, divided by the product of their magnitudes. Second, we saw that the angle theta between two planes is found using the inverse cosine of the absolute value of the dot product of their normal vectors, n1 and n2, divided by the product of their magnitudes. Finally, we established the conditions for parallelism and perpendicularity. A line is parallel to a plane if their direction and normal vectors are perpendicular, meaning their dot product is 0. Two planes are perpendicular if their normal vectors are perpendicular, also meaning their dot product is 0. Mastering these formulas and concepts is crucial for success in the IBAAHL exam. Now, let's move on to some practice questions. Here are 5 practice questions designed to test your understanding at the IBHL level. I recommend pausing the video and attempting them on your own before watching the solutions. Question 1. Find the angle between the plane 2x, y plus z equals 8, and the line x equals t plus 1, y equals minus 1 plus 3t, z equals t. Question 2. Find the acute angle between the planes 2x, y plus z equals 3, and x plus 3, y plus 2, z equals 8. Question 3. Find the angle between the plane 3x, y plus 4, z equals minus 7, and the y-axis. Question 4. The plane pi 1 has equation 4, x-2y plus 5z equals 16. The plane pi2 is perpendicular to the line segment AC, where A is -3, 2, 5, and C is the point where pi1 cuts the y-axis. Find the equation of pi2. Question 5. The planes x plus 5y - 3z equals 8 and 2x plus 2y plus kz equals 9 are perpendicular. Find the value of k. Let's go through the solutions. Here is the solution for question 1. The problem asks for the angle between the plane 2xy plus z equals 8 and the line x equals t plus 1, y equals -1 plus 3t, z equals t. First, we identify the normal vector, n, for the plane as 2, -1, 1, and the direction vector, d, for the line as 1, 3, 1. Next, we calculate the dot product, n dot d, which is 2 times 1 plus -1 times 3 plus 1 times 1. This equals 2 minus 3 plus 1, which is 0. Since the dot product is 0, the normal vector, n, is perpendicular to the direction vector, d. This means the line is parallel to the plane. Therefore, the angle between the line and the plane is 0 degrees. This is a special case where the line does not intersect the plane. Here is the solution for question 2. The problem asks for the acute angle between the planes 2xy plus z equals 3 and x plus 3, y plus 2z equals 8. First, we identify the normal vectors. n1 is 2 minus 1, 1, and n2 is 1, 3, 2. Next, we calculate the dot product n1 dot n2, which is 2 times 1 plus -1 times 3 plus 1 times 2. This equals 2 minus 3 plus 2, which is 1. Now we find the magnitudes. The magnitude of n1 is the square root of 6. The magnitude of n2 is the square root of 14. Using the formula, the angle theta is the inverse cosine of the absolute value of 1, divided by the square root of 6 times the square root of 14. This simplifies to the inverse cosine of 1 over the square root of 84. Using a calculator, the angle theta is approximately 83.7 degrees, so the acute angle between the planes is about 83.7 degrees. Here's the solution for question 3. The problem asks for the angle between the plane 3xy plus 4z equals -7 and the y-axis. First, we identify the normal vector, nin, for the plane as 3, -1, 4. Next, we need a direction vector for the y-axis. The y-axis is a line that goes straight up and down the y-axis. Its direction vector, d, is 0, 1, 0. Now, we calculate the dot product n dot d, which is 3 times 0 plus -1 times 1 plus 4 times 0. This equals -1. The magnitude of n is the square root of 26. The magnitude of d is 1. Using the formula, the angle phi is the inverse sine of the absolute value of -1, divided by the square root of 26 times 1. This simplifies to the inverse sine of 1 over the square root of 26. Using a calculator, the angle phi is approximately 11.3 degrees, so the angle between the plane and the y-axis is about 11.3 degrees. Here is the solution for question 4. This is a multi-step problem. We need to find the equation of plane pi2, which is perpendicular to the line segment AC and passes through point B. First, we need to find the coordinates of point C. C is where plane pi1 cuts the y-axis. This means the x and z coordinates of C are 0. Substituting x equals 0 and z equals 0 into the equation of pi1, we get -2, y equals 16, so y equals -8. Therefore, point C is 0, -8, 0. Now we can find the normal vector for plane pi2. Since pi2 is perpendicular to the line segment AC, the vector AC is the normal vector for pi2. The vector AC is c minus a, which is 3 minus 10 minus 5. This is our normal vector, n, for pi2. The equation of a plane is n dot r0 equals 0, where r0 is a point on the plane. We know pi2 passes through point B, 0, 2, -1. So the equation is 3 minus 10 minus 5 dot x, y, z minus 0, 2 minus 1 equals 0. Expanding this, we get 3x-10y2 5z plus 1 equals 0. Distributing and simplifying, we get 3x-10y plus 20 to 5z 5 equals 0, which gives us the final equation of plane pi 2, 3x-10y 5z equals minus 15. Here is the solution for question 5. The problem states that the planes x plus 5, y dash 3z equals 8, and 2x plus 2y plus kz equals 9 are perpendicular, and we need to find k. This is the same problem we worked through as an example. Let's quickly review the steps. First, we identify the normal vectors. n1 is 1, 5, minus 3, and n2 is 2, 2, k. Since the planes are perpendicular, their normal vectors are perpendicular, which means their dot product is 0. We set the dot product n1 dot n2 equal to 0. This gives us 1 times 2 plus 5 times 2 plus negative 3 times k equals 0. Simplifying the equation, we get 2 plus 10 minus 3k equals 0, which is 12 minus 3k equals 0. Solving for k, we find that k equals 4. This confirms our earlier result. That concludes our session on angles in space. We've covered the key formulas and problem-solving techniques for finding angles between lines and planes and between two planes. Remember, the core idea is to use the dot product of normal and direction vectors. Practice is essential for mastering these concepts, so keep working through problems. Thank you for watching, and good luck with your studies.